Welcome back, soil behavior students. So in this example number 3 of rate of consolidation, we have a soil profile that consists of 0 to 3 meters of sandy silt with a total unit weight of 16 kilometer cube. So let me get that done. Something like this. The silt with a unit weight of 16. Then from 3 to 7 meters, which is total height of 4 meters. Have a clay layer. Gamma t equal to 19. Then below that we have solid rock layer. Rock. While this layer is 3 meter deep and this layer is 4 meters thick. Alright. We got water table that's 1 meter below the ground. This water table that is 1 meter below the ground. Okay. And a sample of 4 meter deep. So a sample that's taken from 4 meters deep. Let's call it point A. We had a sample and we analyzed it in the lab and we got these following results. It had this following void ratio 0.813, compression index 0.62, recompression index 0.15, and sigma dash PC pre-compression stress to be 80 kPa. So we asked to determine whether the clay is normally consolidated or over consolidated. To do that, we need to get the effective stress. So it says sigma V at 4 meters equal to first 3 meters of silt plus 1 meter of clay, and that adds up to 67. We have a pore water pressure. So from this point to this point we have 1 meter plus 2 meters, that's going to be 3 meters of water. Which is 29.4 kPa. Therefore my effective vertical stress is total minus pore water pressure which account for 37.6 kPa. Now when we compare this one to the pre-compression index, it's actually less than that. Therefore, it's over consolidated. It's over consolidated soil. Okay. Part B, we need to estimate the pre-consolidation pressure in the clay layer at a depth of 6 meters. So with depth, CC, CR are fixed, the constant, but the pre-compression stress varies. And actually what stays the same is something called the marginal stress. So the marginal stress, is equal to the difference in the pre-consolidation stress and the initial stress. So that at 4 meters is basically 80 minus 37.6, which is 42.4. Now the marginal stress remains constant with depth. In other words, at any depth inside the clay layer, if I have the initial stress, the initial effective stress, I can calculate the pre-consolidation stress using the marginal stress. Okay, so so basically, if I want to find this one at 6 meters, I need to find the effective vertical stress at 6 meters. So I go at 6 meters. My sigma V is 3 meters of silt plus 3 meters of clay. 105. The pore water pressure is 5 meters times 9.8. 49 kPa. So the effective vertical stress is 105 minus 49 is 56 kPa. Therefore, I could say my sigma PC at 6 meters is the marginal stress plus sigma dash node at 6 meters. So 42.4 plus 56 equal to 98.6 kPa. And that's part B. Part C, if the surface of the site is subjected to a surcharge of 100 kPa, determine the total final settlement of the clay layer due to surcharging. And you should divide the clay layer into two. So we are ordered, we have to divide it into two thick sublayers. So now let's redraw that again. Just the clay layer. We're meant to divide that into two sublayers. And we will calculate the effective stress or settlement in the middle of each one of these layers. So the first half point that will be located at a depth of 4 meters, since the above layer is 3 meters, and now this is 4 meters, so each layer is 2 meters, right? Each layer is 2 meters, and so half of it is 1, so 3 plus 1 is 4, and the other one is gonna be 3 plus 3, that's gonna be 6 meters. Okay, so for the first sublayer, basically we have gotten sigma v or sigma dash naught, which was, let me retrieve that, 37.6, and we could say that the sigma dash final is nothing but the initial plus the surcharge, which is 100 kPa. So it's going to be 137.6. And we have the initial void ratio. Again, let me retrieve this value. It's 0.813. Okay. Well, for the second sublayer, we have sigma dash node, which is 56. Sigma dash final is 156 plus surcharge, and E node is unknown. Okay, because as we go down, we expect that the void ratio is reducing due to compression. So to get this value, it's a bit messy. So I hope I can grab your attention now very well. So let's see. If I draw the E log diagram. Okay. Can I try to imagine the history that point B has gone through? So point B initially had a stress that's the same as point A, which is 37.6. Then deposits occurred and then stress kept increasing until we reach the initial sigma dash PC, which is pre-consolidation stress, which is 80. Okay, sigma dash PC here is 80, while sigma dash PC here is 98.6. So we reached the 80 value. From the 37.6 to the 80, we were following the pre-compression line. See, initially, here we had 37.6, down all the way to 80. So 80, where did this 80 come from? So 80 is the maximum stress the soil has ever seen before. So it must have, during its life, reached the value of 80. Okay, so we must have reached 80. So it must have compressed to 80 now. We must understand this concept. Then after it crossed 80, it's gonna go down using the compression line. It's a bit difficult to draw. Okay, that's the compression line, and that's the recompression line. So until it reached the maximum new point in new stress, which is defined as 98.6. So that's the highest stress the soil has ever seen. Again, so that's 98.6. Then it must have settled back into the new original initial stress that we read currently. So it will recompress using the recompression line. So using the CR slope. Sorry, I should have stopped right here. So this value now that we read is 56, which is following the recompression line. Okay? So now we need to find this E node. Right, so we have to go through CR, then CC, then CR. Three slopes. So delta E, we're looking for, which is this one, right here. Let me... Okay, we're looking for delta E. That's gonna be equal to CR log sigma dash BC over sigma dash node at 4 meters. This is at 4 meters. Plus from sigma dash BC at 4 meters to sigma dash BC at 6 meters. This is sigma dash BC at 4, sigma dash BC at 6. So plus CC log sigma dash BC at 6 meters over sigma dash BC at 4 meters. Plus we went up using the recompression line, CR log sigma dash node at 6 meters over sigma dash BC at 6 meters. Okay, so my delta E, CR is 0.15. Sorry, my CR is 0.15, yes. Log sigma dash BC at 4 meters is 80 over 37.6 plus CC is 0.62 log sigma dash BC is 98.6 over sigma dash BC is 80 plus CR, which is 0.15 log sigma dash node at C at 6 meters, which is 56 over sigma dash BC at 6 meters, which is 98.6. This whole expression simplifies into 0.06 0.0686. Okay, therefore E node at 6 meters equal E node at 4 meters minus delta E. So it's 0.813 minus 0.0686. And that will yield the value of 0.744. Finally, now we have the void ratio of the sublayer at 6 meters. So now the settlement of first layer. We need to do the calculation for that. We need to find delta E. So since this sigma dash node is less than sigma dash BC and sigma dash final is bigger than sigma dash BC, we're gonna use the following formula. Delta E equals CR log sigma dash BC over sigma dash node plus CC log sigma dash final over sigma dash PC, which will be the same formula for the second layer as well. So sigma C sub R is 0.15 log 80 over 37.6 plus 0.62 log 8, sorry, this is 137.6 over 80. That is equal to 0.19, sorry, 0.1952. Therefore, STF in the first layer is equal to the height of the layer, which is 2, times delta A 0.1952 over 1 plus E naught, which is 0.813. That is equal to 0.215 meters. Okay. Settlement of the second layer. We need delta E as well, so it's gonna be CR 0.15 log sigma dash BC, which is 98.6 over sigma dash node 56 plus CEC log sigma dash final, which is 156 over 98.6, and that is equal to 0.16. So STF equal, let's call this STF2, this is STF1. The height of the layer, which is 2 times the change in the void ratio over 1 plus the initial void ratio, which was 0.744. And that is equal to 0.1839 meters. Therefore, I'm running out of space. Therefore, STF okay. Therefore, my final settlement equal STF1 plus STF2. So STF1 was 0.215 plus STF2, which is 0.1839, and finally my total settlement is 0.399. We can estimate that to be 0.4 meters. And that's the end of question 2. Thank you for watching.